Last class, we left off with atomic mass. We were doing a weighted average to find atomic mass. So we were taking the abundance as a percentage and converting it to a decimal by dividing it by 100. So that got us the decimal form, the fraction form, decimal form of each of our three isotopes. This was for magnesium. And then we multiplied these abundances by the mass of that isotope. And we were given the masses of those isotopes. And then that gave us the weighted mass. We added those all together, and we got something that was in between our lowest number and our highest number, the way an average works. For this one, we also could have checked by looking at a periodic table for magnesium. What's the atomic mass for magnesium, or the molar mass for magnesium? It's 24.31, depending on what periodic table you're looking at. So you could expect to be asked how to do an atomic mass calculation on an exam. Moving into some new material, mass spectrometry is a tool that is used to determine the mass of atoms, and you can also use it to determine the percent abundance of isotopes. So the mass spectrometer that we're looking at here on this screen is what I'm guessing that this is a magnetic sector. It looks like a magnetic sector mass spectrometer to me. And so basically this functions. We get a sample that's introduced over here on the far left. There's something that heats the sample up to a really high temperature to make it gas. And then it gets hit with an ionizing beam of electrons in this component here. And that turns these particles, these gas particles, now into a beam of charged particles. Those beams of charged particles get accelerated through these electric plates so that they all pick up the same amount of energy. Heavier things are going to move slower because they all have the same energy. Lighter things are going to move faster. And then it accelerates them around this bend. So it turns them with magnets. It turns them with magnets, and the lighter things are going to get turned more easily with this magnetic field, the same way that they got accelerated more quickly. And the heavier things aren't going to turn quite as much. This is like if you're driving a small car and you try to make a sharp turn, it usually goes decently well as long as it's not too sharp of a turn. But if you were driving like a Yukon or a very large truck and you tried to make the same turn at the same speed, it probably wouldn't go so well for you. You might feel like you're about to tip over. It's a sort of similar thing with the particles here. Basically, this lets us determine the mass of the particles based on how they're spread across the multiple detectors that we would probably have in our instrument. And it also lets us know, based on how many times these detectors get hit, it lets us know how many of the particles we have. So calculate that information. Mass spectrometers, typically very expensive instruments in the hundreds of thousands of dollars range. But they're also very common in labs. So what we might see in a plot of a mass spectrometer, if we put in silver, we would have peaks. The position of the peak indicates the mass of the isotope. So our x-axis for this plot, this is a very simple plot, our mass is AMUs 107 and 109. Realistically, it's more complicated than just mass, but mass is good enough for now. And then the intensity, or the amount of hits that we got on our detector, is the intensity. And these are scaled so that our largest peak is 100%. So it's all relative to our biggest peak. It's not typically displayed in absolute numbers. So 107 is our biggest peak, and 109 is our slightly smaller peak. And the total intensity, the highest peak, highest, tallest peak set to, or is set to, 100%. And we could do calculations with these. So we can take the percent of the isotope we're looking at, in this case Ag107, and we divide that by the sum of ion intensities. And that'll give us the fraction, or the percentage rather, how much of the sample is that isotope. So this silver sample is 51.84% silver 107. And we could use this information to come up with, if we wanted to, an atomic mass for silver generally. So doing the weighted average thing that we saw before. We could come up with the atomic mass for silver. Questions about any of that? I think mass spectrometry is really cool, so if you have questions about how that works, let me know. We won't go into it in depth in class. Okay. So this carries us into molar mass. Molar mass is a concept that we will be using a lot throughout the class, and we're going to use shrimp as an analogy. So shrimp, you may know, are normally sold by count, the number of shrimp per pound. 41 to 50 count shrimp means between 41 and 50 shrimp per pound. A smaller count means larger shrimp. For example, really large shrimp might be 10 to 15 count. So that would be 10 to 15 shrimp per pound. That's a big shrimp. You can also count the shrimp by weighing them. So for example, 2 pounds of 41 to 50 count, since that's shrimp per pound, 2 pounds times this many shrimp per pound would give us somewhere between 82 to 100 shrimp. So if we were like hosting a cocktail party because we feel like being fancy, and we wanted everyone to have 10 shrimp each, right? We could do some calculations about how many pounds of what count shrimp do we need to buy in order for us to have these fancy shrimp cocktails for our party friends. Not something that I would do personally, but something that could be done. We have a better concept or a similar concept for atoms. So as chemists and in chemistry, we may often need to know the number of atoms in a sample of a given mass. And the reason for this is that chemical processes happen between particles. Chemical processes are based on number of atoms, not mass of atoms. So it's the actual number of particles interacting that causes the reactions to move forward. It's not the mass of the particles that causes them to move forward. And since they come in lots of different sizes, we've got 118 different shapes and sizes of elements, of atoms that we can get. It's important that we be able to figure out approximately how many atoms we have so that we can predict what's going to happen or get our reaction to go the way we want it to. So for example, 2 hydrogen atoms combine with an oxygen atom to form a molecule of water. Oxygen atoms and hydrogen atoms are very different sizes in terms of their mass. So hydrogen atoms are much, much lighter, much, much smaller than oxygen atoms, and so if we just put in equal amounts in terms of mass, we would be putting in very different amounts in terms of the number of atoms that we're combining. In order for us to count them in a reasonable fashion, we count them by weighing, or more likely massing, and we can convert mass to atoms, which is what we're going to be learning about next. So when we count large numbers of objects, you may be familiar with units like a dozen. So if you're going to buy donuts for a big party for somebody and something in the morning, you might order a couple dozen donuts, and a dozen is 12 objects. A gross is a dozen dozens, and so a gross is 144 objects, and that's a lot. However, this doesn't even come close to approaching the number of objects that we need to count as chemists because of how small atoms are. So our version of a dozen is the mole. So the mole is our dozen, and we abbreviate it by dropping the E. So it's just MOL. A mole is the amount of material that contains this number. This big number of particles equals 1 mole. And we're typically going to write it in scientific notation. This is part of why we learn scientific notation, because it's a lot easier than writing out this. Or maybe it's one more. So the scientific notation saves us from putting in all these zeros. Probably our calculators won't even let us put those zeros in anyway. And it'd be very easy to get confused. This number is called Avogadro's number, named after Amedeo Avogadro, who came up with the number. We'll typically use a slightly shorter form, 6.022 times 10 to the 23rd. And the benefit, the utility of Avogadro's number is that it lets us count 1 mole is this many atoms, and it usually brings things into kind of our realm of size. So like a mole of copper atoms is about 22 copper pennies. I think a mole of helium gas is like 2 big party balloons. So it brings things kind of up into our scale where it's something that we can we're a little bit more familiar with the size. A tablespoon of water is about a mole of water molecules. The way that we got that specific value is it's the number of atoms in 12 grams of pure C12, just in case you were wondering where that came from. So this also gives us a relationship between mass. The mole gives us a relationship between mass and the number of atoms, and so then we can count atoms by weighing or massing them, putting them on a scale. We can convert between the two. If we are converting between a dozen eggs and eggs, our conversion factor would be built out of 1 dozen eggs and 12 eggs. For atoms, we're going to use this 1 mole of atoms equals 6.022 times 10 to the 23 atoms. And so we can come up with either of these 2 conversion factors, one where moles is on top and the other where atoms is on top. For example, let's say that we've got a pure silver ring, and we know through magic or witchcraft or science that it contains 2.80 times 10 to the 22 silver atoms. We want to know how many moles of silver atoms does it contain. So we're starting with 2.80 times 10 to the 22 atoms. Ag. I usually put the chemical last. And we want to convert this to moles, Ag, moles of silver. Our conversion factor is Avogadro's number. 1 mole of anything equals 6.022 times 10 to the 23. In this case, it's going to be atoms. It could also be other things, but just whatever the singular unit is. And then we have to figure out which of these 2 do we want to be on the top, which one do we want on the bottom. So we're starting with atoms, so this Avogadro's number of atoms will go on the bottom. So our calculation would look like this. We're going to take our large number of atoms of silver, and we're going to divide by Avogadro's number to convert to moles. Our atoms will cancel, and moles and silver come through. And there's a couple of ways that you can put this into your calculator. The way that I prefer to do it is using the dolphin noise key on your keyboard. So we're going to do 2.80, and then we're going to locate the dolphin noise key. What noise do dolphins make? Yep. Right, something like that. So we're going to look for the key that has two E's on it, if you have it, two capital E's. And that'll insert a small capital E. This small capital E means times 10 to whatever follows it. So in this case, we're going to write 22. And then we're going to divide by our 6.022, hit the dolphin noise key, 23. The nice thing about this is that the small capital E connects the 2.80 and the 22, so we don't need parentheses, either on the top or on the bottom. So 2.8 little e 22 divided by 6.022 little e 23, and little capital E, because there's also a little lowercase e. The little lowercase e is like a specific number, and we don't want to use that because you will get the wrong answer. And calculator says 0.04649618 moles silver. We'd round it for 3 significant figures. The other way that you can do it is you might have a times 10 to the power key. And I think you do sometimes have to put these in parentheses or they get screwed up. I think it's most important. I think it's the bottom one that you need to do it on. The top one is not really that important. So that's another way that you can do it. There's probably at least 3 ways that you can put it into your calculator. But you should be able to put this into your calculator and get an answer out. Questions on any of those parts? Cool. So make sure that you can put this in your calculator, get the correct answer out. It'll save us headaches later in the future if we identify those problems now. Okay, so that lets us convert between really, really big numbers of atoms and relatively reasonable numbers of moles, but we still need a way to get to the mass. So we need a conversion factor between mass and moles, and the conversion between mass and moles is molar mass. This literally just means mass of a mole. So an element's molar mass in grams per mole is very conveniently numerically equal to the element's atomic mass in AMU. So all the numbers on the periodic table, not the top right ones, that's our atomic number. Our atomic mass numbers, like for helium 4.00, that's its AMU value. It's also its grams per mole value. They're interchangeable units. So for example, 26.98 grams of aluminum. Aluminum has a molar mass or an atomic mass of 26.98 with units of grams per mole or AMUs, depending on which one we're using. That's going to be equal to 1 mole of aluminum. It's also equal to 1 Avogadro's number of aluminum atoms. That's true for any of our elements on the periodic table. And we can also take a look at the grams of each of these elements that we have. So for example, aluminum is bigger atoms than carbon and helium, so it's almost 27 grams of aluminum to get 1 mole, even though it's the same number of atoms as for carbon and helium. But carbon and helium are only 12 or 4 grams for that same count of atoms, just because of the difference in the size of the atoms. Okay, so the molar mass is what we're going to use to convert between grams and moles. Molar mass converts between grams and moles. For whatever the chemical is, whatever the element is, that's what we're going to be using. So let's say that we've got a 35.8 gram sheet of pure copper. We want to know how many moles is that. So starting with grams, going to moles, what's the thing we're going to use to do that? Molar mass. We need the molar mass for copper. What's the symbol for copper? Oh, are you taking off? Oh, Cu, like the symbol. Yeah, so Cu is kind of behind me here. 63.55 is the number in the bottom left corner, or in the bottom. So that number, 63.55, means that that's the number of grams in 1 mole. So 63.55 grams over 1 mole is our conversion factor. So let's take a look at how we're going to use that for this problem. We're starting with 35.8 grams. We're trying to get to moles. It'd be a good idea to write our chemical in there as well. Okay, so if we put our conversion factor in as written, are the units going to cancel out? No. So if we put it in as written, we'd be multiplying by our molar mass. We need to do what with our conversion factor to get it to cancel? Divide, flip it. Flip what we've got. So the 63.55 will go on the bottom. So we're dividing by 63.55 grams, and the 1 mole part will flip to the top. This gets our grams to cancel, so our units work out correctly. And then we just petition our calculator to tell us one more time, what does the math work out to? We get 0.563. The next number is a 3, so we'll round down or truncate. We're left with 0.563 moles copper. Questions? Great. Okay, so we have tools now to move between a couple of different quantities. We can get to the number of atoms of an element by weighing it, so we can get the mass of the sample. We could go set something down on our balance in the balance room. That'll give us the grams of whatever the element or the compound is. We can find or calculate the molar mass of the element or compound to get to the moles of the element or compound, and then use Avogadro's number to get to the number of atoms. Avogadro's number we're basically just going to be using to go between moles and atoms. We're not going to be using it quite as much as molar mass. So an example calculation for that. How many carbon atoms are there in a 1.3 carat diamond? So diamond is a type of pure carbon. We've got 1.3 carats of diamond. A carat is 0.2 grams. And we want to get to number of carbon atoms. So our solution map, I think carat is abbreviated CT, this type of carat at least. We have a conversion factor between carats and grams. So we can go to grams. Our ultimate goal is to get to atoms. This is all for carbon. What can we do from grams of carbon? Where can we go from there? Yeah, we can go to moles of carbon. Can we get from moles to carbon to atoms of carbon? Yes, we can. So our first step, 1 carat equals 0.20 grams. What do we need to get between grams and moles? Not Avogadros. Molar mass. So we need to find carbon and get its molar mass. Periodic table in class is 12.01. What number goes with the 12.01? What unit goes with it? Grams, and that's in 1 mole. So grams over moles. And then to get from moles to atoms, what do we use? Avogadro's number. Avogadro's number is often shortened N subscript A. So that's 6.022 times 10 to the 23. What's the unit that goes with Avogadro's number? Atoms. And that's equal to 1 mole. So we've got the setup. We just need to make some conversion factors and possibly flip some conversion factors. So 1.3 carat diamond, which is carbon. To get from carats to grams, we need to divide by the 1 carat, multiply by the grams. So grams goes on top, carat goes on the bottom. Carats cancel. We've got units of grams. How do we need to use our molar mass to get rid of the grams? Do we multiply or divide? If we multiply, we're putting it in like it's written. We're going to divide so that the grams go on the bottom. So our grams cancel. And then for our last step with Avogadro's number, we have moles. The 1 mole needs to go on the bottom. And the Avogadro's number part needs to go on the top with atoms. So this gets our moles to cancel. The units that come through are atoms in our last conversion factor and the carbon that we were using at the beginning. So we're going to put into our calculator 1.3 times 0.2 divided by 12.01 times 6.022 times 10 to the 23rd. You can also use that little capital E key. And hopefully you're getting 1.3 times 10 to the 22 atoms of carbon. Questions? I'm going a little slower, trying to go a little slower because we're going to be using molar mass stuff a lot. We'll be doing these type of calculations a lot. So it's important that we get it. All right, to try to visualize how big Avogadro's number is, an Avogadro's number of pennies would cover the entire surface of the Earth to a depth of 300 meters, or a little more than basically 4 football fields deep in pennies all the way around the world. So if you've ever been on a flight or a really long car trip, or if you've ever just traveled a really long distance, imagine everything that you can possibly see for that entire distance being 4 football fields deep of just pennies, but like for the rest of the world. So that's kind of wild. If you took an Avogadro's number of grains of sand, that would cover the state of Texas to a depth of several feet for the entire state of Texas, which is a lot of sand, because sand's really small. It's a lot smaller than pennies. If you counted 24 hours a day for the rest of your life, you would not be able to get even close to Avogadro's number. And here it is with all the commas in there so you can kind of get an idea of how big it is. We'd have thousands, millions, billions, trillions, quadrillions. I think the next one would be like pentillions or quintillions, and then sextillions, I think is what comes after that. So like very large. Hopefully that's coming across. All right, one for you to try, because this has a fun twist in it as well. A titanium cube contains 2.86 times 10 to the 23 atoms. What is the edge length of the cube? The density of titanium is 4.5 grams per cubic centimeter. So go ahead and give that a try. If you can't get to the edge length of the cube, at least try to get to the mass of the cube or the volume of the cube. All right, so we were trying to find the edge length of the cube starting from a number of atoms. We know that it's titanium. We're given a density of titanium. We're told that it's a cube. That's important. We're finding the edge length. Okay, so starting with atoms. 2.86 times 10 to the 23 atoms. What's the symbol for titanium? Ti, capital T, lowercase I. What can we do with atoms? We can convert atoms to moles using Avogadro's number. Can we get from moles to something else? We can do moles to grams. What are we using to get moles to grams? What's the quantity called? What's the name of the thing we're using as our conversion factor? Molar mass. So we're going to use our molar mass for titanium. So we find Ti on our periodic table. It's in group 4, row 4. It's got a molar mass of 47.88. What are the units of molar mass? Grams over moles. Grams per mole. And then from grams, what can we do? Yeah, we can get to cubic centimeters. So we're going to be using the density. Density equals mass over volume, and we'll stop our solution map there for now. So our 2.86 times 10 to the 23 atoms, titanium. We need to use Avogadro's number. We have atoms. Avogadro's number, the 6.022 times 10 to the 23, goes with atoms, so we're going to put that on the bottom. We also have a ridiculously large number to start with, so it's reasonable that we would divide that by another ridiculously large number, like Avogadro's number. Otherwise, the number would be too big. So divide by Avogadro's number, that converts us to moles. Now we've got moles, we need to get to grams. So we're going to multiply by our molar mass. So the 47.88 grams, the 1 mole on the bottom. So our units of moles will cancel out. And then, didn't mean to write equals, we need to use our density. There's a couple ways we can use our density. One way would be the dimensional analysis way. Look at the units of density. Density has grams over cubic centimeters. If we multiplied by that, we'd have grams on top, cubic centimeters on bottom. So our grams wouldn't cancel out. If we divide by our density, 4.50 grams goes on the bottom, cubic centimeters go on the top. And so we can get to cubic centimeters that way, because our grams will cancel. We could have also said, okay, we've found mass as an intermediate. How are density and volume related to each other? Or sorry, we're trying to get volume. Have mass and density. We're trying to find volume. Density equals mass over volume times both sides by volume. Vd equals m. Divide both sides by density. Volume equals mass over density. So we take our mass and we divide it by our density and we get volume. That's what we did anyway. We just did it with a different approach. We did the dimensional analysis path. Okay, and so we'll park at our cubic centimeters. Any questions about any of those steps? So 2.86 times 10 to the 23 divided by, you might want to put this in parentheses, 6.022 times 10 to the 23. Then we multiply by 47.88 and divide by 4.5. 5.053 ... cubic centimeters. We never got rid of the titanium, so we'll just leave it on there. The ... there means there's other stuff. More numbers, but I just am lazy and I don't want to write them. More numbers that I didn't write. And the important caveat, I promise I'll use them in my calculations. So you can use that ... as well. Just know that this is what it means. This means you haven't forgotten there's numbers there. You're going to use them. You haven't rounded prematurely. It saves you some time. Okay, so no questions about how we got to cubic centimeters? Now the fun trick, fun in quotation marks, the fun trick is that a cube has length equal to its width equal to its height. So those are all the same. So length times length times length. It's basically got a volume of length cubed, since length equals width equals height. And so we're going to take the cube root not cube root of cubic centimeters. That's our volume. And that'll give us the edge length. This isn't a question that I'd expect to give you on an exam because it requires geometry knowledge. But I think it's fun. So put a little 3 in the crook of our square root to make it a cube root, and put in our 5.053 dot 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 cubic centimeters, and this will give us out units of centimeters. .72 after we round for 3 sig figs. Questions about any of chapter 2? Great.